Let's just take it out when it comes to photoelectric effect now. Let's just see what happens here. I've got some short info here. Not everything about photoelectric effect, but I've tried to summarize something here for you. You'd see that here I tried to define it. Here you just need to know that photoelectric effect is a phenomenon in science where electromagnetic radiation, and I'm putting in brackets here light, because light is actually an electromagnetic radiation. So when light causes electrons to be ejected from a metal surface, we call that phenomenon photoelectric effect. Now, if a light can cause electrons to be ejected from a metal surface, this tells us that this light consists of some packages or particles, something that we can even say they might be having some mass in them. Now, these packages, we call them photons. These are photons of light, and they carry specific amounts of energy. And how do we get that amount of energy carried by a by a photon? The amount of energy carried by a photon can be calculated using that equation there. We call it the Planck. We call this the Planck's equation, E equals hf. This f is the frequency. Now, frequency, you would know that frequency has something to do with waves. Remember the wave equation, C equals f lambda. Okay? Now, from this, we can understand that frequency should have something to deal with the wave nature of light. But the moment we begin to talk about light having packages of energy, we are beginning to say that light has got a particle nature. In other words, the photoelectric effect is actually the phenomenon in science that tells us that light has got a particle nature. Now, when we talk of light as a wave, when we look at C equals F lambda, there you would know, in fact, that we're using V equals F lambda, but V and C are the same. I will come back to why we're using C here. Now, when we use the wave equation, we are saying that light has got a wave nature. So what brings them together is because we're talking frequency, we're talking lambda wavelength. Now, when do we make use of C? C is a specific speed of light, and we call it C. It is a constant. It is 3 × 10⁸ meters per second in a vacuum. Now, when we say that these photons of light are actually making up the light and they're containing energy, we say that this energy is actually the same for every photon of the same light. We say that that energy is quantized. So if we're talking about photons of green light, for example, all of them, each one of them will have the same amount of energy as the others. So we say that energy is quantized. It's the same for every particle of light. Now let's move on quickly to something important that we need to talk about, and I bet it could be in the exam: work function. Now, what is work function? We call work function the minimum energy required to emit electrons from a metal surface. So you need a specific amount of energy for a specific metal to eject an electron from that metal. But remember, that light that will be shining on that metal surface will be sending in packages of light called photons. These photons will be heating the electrons, transmitting that energy into them, and the electrons will be absorbing the energy and getting ejected from the metal surface. Now, for every electron, we need a photon to be ejected. You can't have two photons ejecting one electron. So if there's two photons, we should expect two electrons to be ejected. Now, let's now move on to something very important around work function. When we talk work function, like I've said, the minimum energy required to emit an electron or to cause an electron to be ejected from a metal surface. If that energy is just that minimum, remember that energy is hf, it will be equal to the work function. We use W naught as a symbol for work function, and that will be hf naught, that's the energy needed to remove any electron. So if the energy brought about by the photon equals the work function, we would have electrons being emitted. But we can have a situation where this energy brought about by a photon is actually less than the work function for that specific metal. If it is less, we will have no electrons emitted. That is very important for you to understand. Now, there is also another situation where we may have the energy brought by a photon greater than the work function. If it is greater than the work function, we expect, of course, electrons to be emitted. But then, when they are emitted, remember that this HF is now greater than the work function. There should be some energy left out after that. What happens to that energy left out when part of the energy has been used to overcome the work function of the metal? Now, this is what is going to happen. Part of that energy will be gained by the electron as kinetic energy. In other words, it will cause that electron to move, to gain speed. We'll see it floating. Now, therefore, we can sum up whatever we're talking about here through this equation and say the energy contained by a photon with energy greater than the work function will therefore be equal to the work function, the energy needed to overcome that the work function of the metal, and the remaining energy gives that electron some kinetic energy. Remember, kinetic energy, energy of motion, getting the electrons to move. So that is what is happening there. Now, if we have electrons moving, it means, remember that EK is given by half mv squared. Now, if it's an electron moving, you must always remember that that means your m here is the mass of the electron. And this is given to you in the information section of the physics paper. So always look out for it when you are to calculate for it. Okay, so you must get the mass of the of one electron there and substitute m for it there. It will normally not be given to you in a question, but then they know that it is given to you in the information sheet. I think that I think we'll get back to this section again, perhaps looking at questions afterwards.